Okay, so let's continue our discussions related to this particular course on Introduction to Electronics. So today we start our discussions related to the last module of this particular course, which is digital circuits. And we have discussed earlier, right in the beginning of the course, that most of the signals that we pick up from our environment they are analog in nature. And analog meaning that their value varies continuously. They can take up any value in a certain range. And in this particular case, for example, our signal can take any value between 0 and 1. And the signal is continuous in time and can take any value in a particular range here. And so that's an analog signal. And let's convert this analog signal into a two-digit number. Okay. And so these two digits are the following. So for example, let's say the voltage at this particular point is 0.67 volts. So the two digits will be, this is the most significant digit, 6, the first decimal place, and this is the second decimal place, 7. So we convert our number into this is some converter circuit. Let's not get into the details of how we build it right now. So we convert it into a two-digit number here, and each one of those digits, these are decimal numbers, so obviously they can take values, any discrete values from 0 to 9 here. All right, so we are converting it into a discrete number here. So for example, let's say if there is a voltage 0.45, then the first decimal place is 4, the second decimal place is 5, so we will get 4 here and we will get 5 here. So we'll get two numbers, 4 here and 5 here, maybe 45 here. Similarly, 0.75 here, so 7 is the first digit here, 5 is the second digit here. Note that we are converting it into a two-digit number only. So similarly, we get 0.932, so the first is 0.9, the second digit is 3, and the 2 is, we are rounding it up because it's a representation only in two digits, so the 2 is ignored, and we get 93. 0.934 is also converted into 9 and 3. 0.936, well, we round it up, and this is closer to 0.036 is closer to 4 here, 0.04. So we round it up into 9 and 4 here. So we are taking a signal, an analog signal, which is varying continuously, can take any value between 0 and 1. Note that it could be 0.934, 0.935, it could be anything. But we are converting it into a two-digit number here, a two-digit number. Each digit is a decimal digit, can take any value between 0 and 9. All right, so there is a loss of accuracy as you can see here. 0.932 is also represented as 9 and 3. 0.9434 is also represented as 9 and 3 here. So there is a loss of accuracy. We are not able to, after we convert it, our signal at the output is not able to differentiate between 9.932 and 0.934. And similarly, if it had been 0.931 or 0.933, we will not be able to differentiate. All of them would be represented as these two digits as 9 and 3 here. So there's a loss in accuracy. Whenever we are converting an analog signal into a digital signal, in this case two digits, there's a loss of accuracy. And as you can imagine, we can increase the accuracy by taking, let's say, a 3-digit representation. Okay, so then that would have been accurate to the third decimal place. So depending on how accurate we want the conversion process, we can take 1 digit, 2 digit, or 3 digit, that is. So what is the advantage of doing it? Why introduce, note that when we are converting an analog to digital, we are seeing examples that we'll always have a loss in accuracy. No matter how many digits that I take, there would always be something that I would be ignoring. If I take a 3-digit number, I would be ignoring the effects of the fourth decimal place. So there's always a loss in accuracy. So why convert it into a digital signal like this? Why not just live with the analog signal here? So let me give some examples of how using digital signals can be advantageous. The first one is a very important point, which is that once you convert a digital signal, the digital signal is very robust to presence of noise, while the analog signal gets corrupted very easily. So let's say this is our analog signal, and let's NT is a noise. So let's add the noise, and the noise is a random signal, and let's say the noise can lie anywhere between minus 0.2 to plus 0.2 here. Okay, and so that noise gets added here, and the various sources of noise. We mentioned briefly that almost every electronic component, every resistor, every diode, every transistor, they're all sources of noise. And then the power supply we have seen may have some ripple, and ripple is unwanted. So that's also like a noise, unwanted thing. That's a noise here. And there are various environmental sources of noise. If you have imperfect switches and when you switch something on and off, those switches also radiate noise, and the noise can then get into your circuit. So there are various sources of noise that are there here. So suppose our original signal was 0.45 volts, and it gets corrupted by noise which lies anywhere between minus 0.2 to plus 0.2. Well, then after addition of noise like this, the final signal would lie, depending on the magnitude of the noise, anywhere between 0.25 to 0.65. And it's very difficult now, once the noise gets added to it, it's very difficult to tell what the original signal was. Whether it was, so when you obtain let's say 0.35 at the output, when you obtain 0.35, is 0.35 the original signal, or 0.65 is the original signal, or 0.55 is the original signal? We have no way of knowing, because the noise is completely random. So now, of course, noise is random. The property of a noise is different from the property of the signal, and we could take advantage of that. And we have seen briefly in an earlier lecture that we could use some kind of a filtering to reduce the effects of the noise, and we could reduce it, but we cannot eliminate it. Okay, and so and in some situations it may become the property of the noise. We may not be able to differentiate very well a noise from, let's say, a speech signal or some other signal that is coming from some source here. So the point is that once an analog signal gets corrupted by noise, it becomes very difficult to recover the original signal. We may reduce the effects of the noise, but you can't recover the original signal. All right, so let's see how a digital signal will be much more robust towards noise here. So we have this original analog signal. We are converting it into a 2-digit number here. The most significant, the first decimal place is 4 and 5 here. Okay, so there's a converter circuit. Let's say we have convert. So we'll consider what happens to a digital signal like 4, 5 when we add noise to it. So note that 4 is a 4 volt and 5 is a 5 volt here. Okay, and so let's add noise to it. So noise lies anywhere between minus 0.2 to plus 0.2. So 4 will become, that signal after corruption by noise will lie anywhere between 3.8 to 4.2. Similarly, 5 will lie anywhere between 4.8 to 5.2. Now what we do is we have a decision circuit. The decision circuit decides which the voltage that you get here, which voltage is it closest to? Is it close to 4? Is it close to 5? Because those are the digits that we have, 0, 1, 2, 3, 4, 5, up to 9. So it decides which the number that you get here is closest to which particular digit. So for example, 3.8 or 4.2 is closest to 4. So the decision circuit will give a voltage output as 4. Similarly, in this case, the decision circuit for this input will decide which digit is it closest to. 4.8 and 5.2, both of them are closest to 5 here. So it will give an output 5 here, 4 and 5. Right? So even though we added a noise to it, minus 0.2 to plus 0.2, note here, we get 4 and 5. And then we can combine them together. This converter circuit took an analog signal and split it up into 2-digit number here. Now that we have a 2-digit number here, digital number, we can convert it into an analog number again, some reconverter circuit here, which is inverse of this particular one, and we can get back 0.45. So the point is that if you have a number 0.45 and you were going to transmit it from A to B, and along the route, let's say there's a source of noise, right? So when you transmit 0.45 directly, well, the noise gets added and you may have anything between 0.25 and 0.65 and you have no way of knowing. But then if you digitize it like this here, 4 and 5, and then the noise may get added, but then you can recover it and you find that the final signal is 0.45. So despite the presence of noise, a significant noise, minus 0.2 to plus 0.2, we are able to recover the original signal back here. So that is what we mean by that, so the signal, note that is corrupted. So this is 4 and 5. The signal is corrupted 3.10 and 4.2, but we are able to regenerate the digit that is there here, because all we need to do is look at which digit is it closest to. And despite this presence of noise, we can easily see is closest to 4. Now, of course, the noise, if the noise had become, let's say, minus 0.6 to plus 0.6, then, of course, then it would have been difficult to tell. We could have made errors here. But then you need very large amount of noise to create an error in this particular digit. And similarly, very large noise to create an error in this particular digit. Because the digit is a large number, 4 volt or 5 volt or whatever. Okay. So you need large amounts of noise to create an error in this. And so through the decision circuit, we are able to regenerate it and get back the original 0.45. So this is just a simple example to illustrate that when noise gets added to an analog signal, it becomes difficult to determine. So if you're wondering, well, we have taken 0.45 while here it is 4 volt here. Well, suppose we had taken 4 volt here, 4.5 or 4 volt here. And 4 volt we add noise to it, so it becomes 4.2 or 3.8. Well, we have no way of now recovering what the original analog value is. Was it 4 volt? Was it 4.1? What was it? We have no way of recovering unless we use some kind of a filtering or something to eliminate the effects of the noise. But we are not looking at the elimination of noise at present. We are saying that analog signal, once corrupted by noise, then we have no way of knowing what the original value of the analog signal is. While here, well, we can recover. All right, so we said that, for example, when we take an analog signal and we convert it into a digital signal, there's a loss in accuracy, because if you're using 2 digits, maybe you're losing the information that lies in the third and the fourth, the higher digits here. But note that we just saw, for example, if we took 0.452, the analog signal here, 0.452, and when we add noise here, we'll get anywhere between 0.252 and 0.652 here. And yes, when we take 0.452 and we convert it into a 2-digit number, 45, but then at the end of it, despite the presence of noise, we are able to get 0.45. So here, when we add noise, we are uncertain even about the first decimal place, right? So here, at least, yes, we lost the third decimal place, but we recovered 2 digits properly, okay? So still this particular circuit, this method is more accurate as compared to a simple working with analog number, especially when there is a significant noise that is there. All right, so overall higher accuracy we obtain as compared to working with only analog numbers here. And note that if you want, we could use a different converter circuit and maybe work with 3 digits, 4, 5, and 2. And now you can add, to each one of those digits that is there, you can add noise to it. You can add noise to it. You can add noise, same minus 0.2 to plus 0.2. You can add these noises that are there. But then the decision circuit again will look at which digit does it lie closest to, and will regenerate those numbers, 452. And you combine them together and you get 0.452 here. Right, so you are able to get back despite the presence of noise. So you're sending a signal, and despite the noise getting added to it, you're able to recover the final value here. And as we are trying to tell that when you're converting an analog into a digital number, there is a loss of accuracy. But then depending on your application, depending on your interest, you can decide how many digits are sufficient for you. If 2 digits are sufficient for you, then that's fine. But if you need more accuracy, well, you can do a 3-digit conversion. You could do a 4-digit conversion. Okay. The other point is, so besides robustness to presence of noise, the other point is processing. So suppose you have a signal and you would like to multiply by 2. So we saw a circuit in the last lecture. We saw a circuit, you can build a circuit like this, a non-inverting amplifier with a gain of 2. And you can get the, try and get multiplied by a factor of 2. But note that, so this is a schematic with perfect resistors. In practice, resistors will have tolerances. And suppose these are not exactly, this is not exactly 1K, but maybe a little less than 1K. This may be a little higher than 1K. And what you end up getting is a gain of 1.9. but you really wanted to multiply your input signal by a factor of 2, but you're getting multiplied by factor of 1.9. So for example, if I have a signal 0.44 volts, well, we would get 0.836 instead of 0.88, and there is an error here. And depending on the nature of the application, this error may be significant, right? So we're not able to do the processing accurately because gain of 2 multiplication by 2 is not accurate because of the tolerances of the resistor, and there could be other reasons as well. Now let's see how we can do it. So we take our original signal VI, analog signal, this analog signal that is there, convert it into 2 digits, right? So the first decimal and the second decimal place. Now our goal was to multiply VI, right? Multiply VI, so 0.44, our goal was to get 0.88. So we have separated it into 2 digits. Let's multiply this. This is a voltage, so let's multiply it by 2, and let's look at it here. So let's go forward. So 0.44. So we separate it out into 2 digits, 4 and 4. Let's multiply by 2, but we note that multiplication is not very accurate. So let's we assume that the gain is 1.9 here. So when we multiply 4 by 1.9, we get 7.6 here, obviously because of the error here. But we use a decision circuit. The decision circuit decides which number is it closest to. So it's close to 8. And similarly, this is close to 8. And then we combine them together and we get 0.88. So note that despite the error in multiplication that you see here, we are able to multiply this accurately and get the accurate result here, 0.88 here. 0.44 multiplied by 2 gives us 0.88 here. So, in the previous case, we had noise that was causing problem for us. In this case, we have error. And we have error which is causing problem in doing accurate processing. But then again, the moment we convert it into a digital signal here, we have this property that the digital signal, yes, the voltages will still get corrupted. But we have the property that we can regenerate it back here. So 7.6, we regenerate it using a decision circuit because we are only working with discrete numbers. Our interest is in which digit does a particular number belong to. Is it 0, 1, 2, 3, 4 up to 9 here? And therefore, even if it becomes 7.6 or it is 7.4 or 7.3, it does, if it becomes, as long as it is more than 7.5, right? As long as it is more than 7.5, 6, 7, 8, 9, anything it could be, the number would be 8. So it is robust to errors, is robust to noise up to a particular point, obviously. If the errors and the noise become very large, then of course there would be a error in that particular digit, and instead of 8 you may mistake it for a 7, and then then of course you will get an error. But later on, as you may see later on, perhaps not in this course but other courses, there are ways of even correcting for that. When a complete digit flips, instead of 8, if it becomes 7, there are ways of even correcting for those aspects also by using error correcting procedures here. So not only can you do accurate processing, the processing of digital signals is often much simpler. You have to build circuits like this to just multiply by 2, and to multiply by or divide. For example, if you wanted to divide something by 2.5 or so, it becomes more complex. So working with analog signals, doing processing on analog signals, multiplication, division, and all of those, in principle we can do it, but in practice it is not very easy. While with digital signals, we'll see the processing of signals, once you represent them as numbers, it becomes very, very simple. And because it becomes so simple, the processing of numbers in digital format, then you can do very complex information processing. An example of complex information processing is that you can build a circuit, for example, that can beat a chess player. So this is old. All of you must have read about, again, basically a computer with an algorithm. So computer is nothing but a circuit, programmable circuit. So a programmable circuit, recently, that it beat the champion in that game of Go. All right, so all that you can do because digital circuits allow much more complex information processing. So working with digital signals is easier. Multiplying digital signals, adding digital signals, all of those things are much simpler. So, so we had seen this diagram right in the beginning of the course. So, so our goal of building a circuit is to create a positive change in the environment. It may be to just amplify an audio signal or transmit a video signal and all kinds of things. So it involves signals from the environment, as we've been saying, are mostly analog in nature. And so signals are converted into electrical, and you can do analog signal processing and then convert it back to the appropriate signal in the environment. So, all right, so we have seen this kind of a thing. And what we've been saying is analog signal processing is not as easy, more difficult. And also analog signals are, once corrupted by noise, it's much harder to recover them back. And so for that reason, what we are saying is that best is easier and best to, when you convert a signal to an electrical signal, it may be analog, but use a analog to digital converter, convert it into a digital signal. Do all the processing in the digital domain, and then take your digital signal, convert it back into analog, and then you can use an actuator and come back to the environment, let's say. So an important part is generating the digital signal, this digital signal here, or taking a digital signal and converting it back into an analog signal here. So let's look at briefly what is involved. The actual circuit for doing A to D conversion, we'll look at it towards the end of the course if time permits. But look at the steps involved in taking an analog signal and converting it into a digital signal. So let's stay with the example. So we have an analog signal here, xt, and we want to convert it into 2 digits here, 2 decimal digits here. And let's say the analog signal is here. Xt is some 0.5 plus 0.5 sine 2 pi 10 power minus 3t. So the first step in converting a analog signal into a digital signal is what we call as sampling. So we take a signal, which is shown here, and we sample it at discrete intervals of time. Okay, so we sample it, which means that at this particular point, we capture the signal here. Whatever is the value of the signal at this instant, we try to capture it. Similarly, whatever is the value of this instant, we try to record it. So we sample it at certain intervals. Let's say for a sinusoid like this, we want to capture the entire sinusoid. So let's say we sample it at intervals of t by 12, right? So we have 12 samples here. And let's say those samples are, when we sample it is 0.5 here, is 0.75 here, and let's say these are the samples that we get here. Okay. So how do we do sampling? Well, we could do a sampling using this particular means here. So we have a switch and we have a capacitor. So suppose you want to sample at this particular instant. So you close the switch. You close the switch. The switch could be a MOSFET. And we've seen earlier that MOSFET can be in a high impedance state or a low impedance state. So when you close the switch, then what happens is the signal xt charges up the capacitor very quickly. So the capacitor will charge up to this particular voltage. And then the switch is open. So we get these discrete values that are there, sampled at, let's say, uniform intervals of t by 12. And these values are available on this particular output node here. And so this is what the whole thing looks like. So this is the original sinusoid that is there here, our signal. And we pass it through a signal like this here. And at the output, this is what we get here, at the output here. So note that once it is sampled, once you sample it, the capacitor charges to the value of the sinusoid at that instant. And it retains that. Obviously the capacitor cannot discharge, so it retains that particular value. So that's why it is constant till the next sampling instant. In the next sampling instant, it samples the next value here, so quickly charges up. So the charging is so fast, that's why we have shown it almost like a vertical line here. And then it holds the value till the next sampling interval. So that's why we call this circuit as a sample and hold. So this is the sampling part. Once the switch closes, we are sampling, or we are trying to find out what the value of the signal is at that particular instant. And then once the switch is opened, it holds that particular value till the switch closes again here. So we call this as a sample and hold circuit here. And as I said, the switch can be implemented using a MOS transistor. All right, so now if you're wondering that, note that once you have sampled a signal like this, can I recover back the original sinusoid? And the answer is yes. So if I take my sample signal and I pass it through a low pass filter. So this is my original signal here, and this is my sample signal here, right? So passing it through a RC circuit like this here, basically a switch and a capacitor circuit like this here. And note that, so this particular signal, you can obviously see it has this fundamental component that is there here, the sinusoidal part here. And it has, because of these rapid changes here, it has some high frequency components. And if you pass it through a low pass filter, you will remove all those high frequency components and you can recover it back here. You can recover back the sinusoid that you see here. The details we'll ignore in this particular course, so the entire filtering process and all of that, but it can be very simple RC filter here, low pass filter here, and which will give you the sinusoid that you see over here. Right, so yes, we can sample a signal and get a signal of this kind, and we could, if you want to recover back the original signal, well, you could pass it through a low pass filter and you'll recover back the original signal also. All right, but our goal is not just to sample and hold a particular signal. That's the first step in our conversion process. We would now like to convert it into a two-digit decimal number here, okay? And so what we do is, that particular process is what is called quantization. So right now, after sampling and hold, we have still an analog value here, and this value could be anything between 0 and let's say 2 volt here. It could be anything in that. Now we would like to convert it into, we would like to quantize it. So we would like to convert it into two discrete values, two decimal values here. And so we call this a quantizer, and quantizer could be, depending on the accuracy that we desire, it could be 1-digit quantizer, 2-digit quantizer, 3, 4, 5, 8-digit. It could be anything depending on the accuracy that we desire here. If it's a 1-digit quantizer, then for each sample point, for a sample point like this here, we'll have a digit 0. For a sample point here, we may have some other digit, and like that, each one of those sampled values is converted into a single digit like this here, 1-digit quantizer. 2-digit quantizer, as we said, 2 digits are used to represent each particular sampled voltage here, 0, 0, 1, 2, and so on and so forth here. All right, so basically what a quantizer does is, so the values that we have sampled, let's say they lie between 0 and 2 volt. They lie anywhere between 0 and 2 volts. So what a quantizer is doing, if we are talking about 1-digit quantizer, so it's 1-digit quantizer basically means like you would like to classify this xn into either a 0 or a 1 or a 2 or 9, right? So that's what 1-digit quantizer means. So what we do is our 0 to 2 volt scale, we can divide it up into 10 parts, 10 intervals, first interval, second, and up to the 10th interval. And now all we need to do is figure out, so these are the intervals. And if my signal, the sample signal lies in this particular interval, we'll say, we'll represent it by digit 0. If it lies in this particular interval, we'll represent it by digit 4. If it lies in this particular interval, we'll represent it by digit 9 here. So all we need to do is figure out now which interval does it lie in. Does it lie here? Does it lie here? Or does it lie here? And then, this is a 1-digit quantizer, and then appropriate number will be, digit will be assigned to it. Okay. So it's obvious that quantization introduces errors, right? So for example, if the number here, let's say, is, if we're talking about anything which lies between here and here, let's say 0.4 to 0.6. So let's say it is 0.5. So if it is 0.5, we'll assign the digit, let's say 2. If it is 0.55, we'll again assign the digit 2. If it is 0.58, we'll again assign the digit 2. Or if it is 0.43, we'll assign the digit 2. So all of them are being assigned a digit 2 here, right? So that way, of course, there's a loss in accuracy. There is an error that is being introduced because of the quantization process. And you could reduce the error by by doing a finer quantization, by dividing this 0 to 2, let's say in 100 parts. And when you do 100 parts, then you have 2-digit quantization. You will require 2 digits, 88 or 89 or 95 or whatever, to represent it. If you want, and then you could do even finer quantization. You could do a 3-digit quantization. Then you divide the scale from 0 to 2 volt in 1000 parts, in 1000 intervals. All right, so let's, okay, so this was the signal that we have. And this is how we are quantizing. We quantized the whole thing in a 1-digit quantizer. We quantized into 10 intervals, and the first interval is 0 to 0.2, and so on and so forth. Final interval is 1.8 to 2. And so this, so after sampling, this is the signal that we obtained. And now this is what the quantizer will do. Depending on the value that you see here, for example, if I see 0.5, and 0.5 lies here between 0.4 and 0.6, so we will assign a digit 2, right? So 0.5 will assign a digit 2. 0.75. 0.75 lies here, so we'll assign a digit 3. Like that, for example, let's say 1. So 1, when we look at 1 volt here, 1 volt lies in this particular case here, 1 to 1.2. So we take, so when we write a interval like this, so it is 1 or anything larger than 1 up to 1.2 here, okay? So 0.5 1 volt, we will assign it as 5 here. So like that, we can assign the digital number here. Right, so that's how we obtain a final a digital number starting from an analog number here. So the first step is sample and hold, convert it into a discrete, sample it at discrete intervals of time. So, and then after that, do a quantization. Right, so 0.5 here, and then gives us a digit 2 here. 0.93 gives us a digit 4 here. Well, as we said, you can do a 2-digit quantization. You divide it up into 100 intervals like this here, and then assign 2 digits 0001 and up to 99 here. And 2-digit quantization is also similar, right? So 0.5, well, you will assign it. You can go back to this table here. 0.5, you assign it a number 25 here. 1, you assign 50 here. 0.75, you assign 37, and like that. A pair of digits is assigned to each analog voltage here. Okay. 0.93 is assigned 46 here. Okay. So after getting a digital signal, can we convert it back to the analog signal here? So we said we just saw how to convert it into a digital signal. And then what is involved in converting it back into a analog signal? So let's just take a very simple case where we don't do any processing. We convert into xn and no processing, so yn equal to xn. And let's see whether we can generate back the original signal here. All right, so this is our xn, the signal that is there, a 1-digit quantizer. So these are the digits that are there here. And so when we get a number like this 2, what we do is, because remember our scale was a 2-volt scale, and we divided it into 10 parts here, and each interval was about 0.2 volt, because when you take 2 volt and you divide it by 10, you get 0.2 volt here. So if you want to convert it back into a analog voltage, so when you get a 2 multiplied by 0.2, so you get 0.4. When you get a 3, you multiply it by 0.6, you 4, and so on and so forth. So you get what, whenever you get a number, you multiply it by that interval in terms of the voltage that is there. So each interval is for us 0.2 volt. And so you get these analog voltages that are there. And of course, you get it at discrete intervals of time here. And the original analog voltage was 0.5. If you recall, we had 0.5 and we had converted into a digital number 2. Now we're converting it back into an analog number. So we multiplied by that interval, we get 0.4 and we get 0.6. So obviously there's an error, because there was a loss in accuracy. When we took an analog signal and converted into a digital number, there was a loss in accuracy. And we take the digital number and convert it back into an analog number, we can obviously see the loss in accuracy. 0.5 versus 0.4, 0.75 versus 0.6. So these are there. But if we did a 2-digit quantization, So we divide the whole scale from 0 to 2 volt in 100 parts. Each part is now note 20 millivolts, because 2 divided by 100 is 20 millivolt here. So each part is 20. So now when we, we had a 0.5 analog voltage. When we convert it into a digital number, we assigned it to 5. Now, if you want to convert this digital number back to analog, you have to multiply by this interval 0.02. So you multiply by 0.02, you get 0.5. So in this case, it's perfect. 0.75, the digital number is 37. You multiply by 0.02, 0.74. Well, there is an error in the second decimal place. 0.93, we get 0.92. 0.75 we've already seen. 0.25 we get 0.24. 0.067 we get 0.06 here. So there is a inaccuracy in the second decimal place. First decimal place is fine, and there's a little bit of inaccuracy there. If you want more accurate, then what we would have done is we would have divided the whole scale into 3 digits, and then it would have been accurate to the second decimal place, and we would have had errors in the third decimal place here. So note that conversion, we've already seen how to convert an analog signal into a digital signal here through sample and hold and then quantization. And then the digital number, if you want to convert it back into an analog voltage, it basically involves multiplication with this step here. Each step is 0.02 in this case. In earlier case, it was 0.2 volt. So it multiplies and then you get here. Okay. Now, we've been talking about digits. We said you can take an analog signal, convert into 1 digit and 2 digits and 3 digits. But decimal number is not really convenient. It's convenient for us when we do our maths and arithmetic, but it's not convenient to build circuits to work with decimal numbers. Right? So, for example, we talked about this kind of a circuit. You take an analog signal, convert it into 2 digits, and then you multiply them together, and then you use a decision circuit and reconvert it. These kinds of circuits are harder to build when you work with decimal numbers. Okay, while we will see that they're much easier if we work with binary, because binary has just 2 values, 0 and 1, while our decimal number we have to work with 10 digits, ranging from 0 to 9, and that makes the processing more difficult and cumbersome, and we lose some of the advantages of working the digital domain. So the full advantages of digital domain come when you represent the number in a binary arithmetic as only 0 and 1. So just to illustrate, for example, how do we add 2 plus 5? Right? So working with the digit 2 and the digit 5, and we want to add up the 2 digits. Well, we'll have to represent 2 in the form of, let's say, a voltage 2 volt, and we'll have a voltage 5 volt, and we'll build this circuit that we have seen here. And we may do 2 plus 5. Well, how do we add a 2-digit number, 23 plus 45? So you may think of 23 plus 45. So you may think, well, let's build a circuit for the first digit, and then let's build a circuit for the second digit. So first digit is here, second digit is here, and we could do that. And so you have to build all these amplifiers, resistors, and all of that you see here, and these are far more complex than what we will see, the circuits that we require here. How do we add up 23 plus 58? So in this case, 8 and 3, and then there's a carryover, so we need an adder here which will give us the sum, and there has to be a carry, and the carry has to be fed into for the second digit here, which adds up 2 and 5, and there's a carry also here. And so doing all of that with when the voltages are when the digits range from 0 to 9, so those 0 to 9 have to be represented in these numbers, voltages, 0 volt or 2 volt or 3 volt and all that, and then the circuits become complex when you have to add up digits which are ranging from 0 to 9. Then so the circuits are almost like then the analog circuits. Okay, so it's not easy to design circuits to carry out this operation using decimal system. And and as we said, if you convert your analog signal into a digital signal, but not in the decimal notation, but in the binary notation, then things become very simple here. Okay, and much more convenient. And so that's where we will begin our next lecture. And for example, we'll end with just showing you very quickly that when you use the decimal, when you use the binary system, then the analog to digital converter is fairly simple. These are the sample and hold part here, sample and hold. There's a comparator and some logic circuits and all that. And this is a circuit which can convert a digital number in binary format into an analog format here. As we said, if time permits, we'll see how these circuits work, which allow us to convert an analog to digital signal and a digital to back to analog signal here. So let's stop here.